Hi, in the last video I explained what eigenvectors were and explored their fundamental definition and how they emerge in mathematical context. I will do a quick recap before explaining how eigenvectors are used in real-life scenarios in fields such as science, engineering, including data science. So let's make a start. Consider this column matrix 2, 1. It has 2 rows and 1 column. This matrix can be considered a vector in 2-dimensional space. This means it has magnitude, which is the length of the vector, and it has direction, which is the angle it makes with the x-axis. Now let's say I have another matrix 5, 4, 2, 3, and I multiply this matrix with the vector. The resultant vector will be 14, 7. And if I plot this new vector 14, 7, it will look like this. Its length has increased. The new coordinates are 14, 7, but its angle still remains the same, 26.6 degrees. So this new vector 14, 7 can also be written as 7 multiplied by 2, 1. Isn't 2, 1 the original vector we started off with? Its magnitude has increased by a factor of 7, but its direction still remains the same. So this vector, which only increases or decreases in magnitude but does not change its line of action or direction, is called eigenvector. And this vector 7 is called eigenvalue. This eigenvalue only changes the magnitude of the vector. It either increases or decreases it. It does not change its line of action or its direction. So we can say that this only scales the original eigenvector. So it is in fact a scaling factor. And this matrix over here is called linear transformation matrix. Why? Because it linearly transforms the vector to which it was multiplied with. In our case, it transformed its magnitude. Now, a linear transformation matrix can also change the direction if it is multiplied with a vector, if that vector is not an eigenvector. So what happens if I change the linear transformation matrix and use this new matrix now? 6, 4, 2, 5. Now the result will be 16, 9. Now if I plot this, it gives me this vector. You can see that the vector has increased in magnitude and it has also changed its direction. Its angle is now 29.4 degrees with x-axis. Its magnitude has also increased. So now this vector is not an eigenvector because it has both changed its magnitude and also changed its direction. So this is very important to note. If a vector changes its direction and also changes its magnitude, it is not an eigenvector. For a real-life example of eigenvector, let's take the population of rabbits. Let's say that rabbits in a particular area have had a virus outbreak. Some rabbits will get infected, some rabbits will recover after getting infected, and some rabbits will remain uninfected. Let's say the total population of rabbits is 100. Now let's say on day 1, 5 rabbits get infected. It means that healthy rabbits are 95 and infected are 5. On day 2, 10 more rabbits get infected on top of the 5 that are already infected. But out of the 5 rabbits that were already infected, 2 rabbits recover. So there would be a total of 13 infected rabbits and 87 healthy rabbits on day 2. And this back and forth between infected and healthy rabbits will keep going for a few days. After a few days, the population of infected and the healthy rabbits would stabilize, such that there would be 70 healthy rabbits and 30 infected rabbits. What this means is that on that day, 5 rabbits would get infected and 5 would recover. So the total number of the infected and the total number of the healthy rabbits remain unchanged. Any day after that day, there would be no change in the population of infected and healthy rabbits. If 5 rabbits get infected, then 5 rabbits will recover. If 3 rabbits get infected, 3 rabbits will recover. And the total number will remain the same, with 70 being healthy and 30 being infected rabbits. And this proportion remains largely unchanged over the next few days. So this population of healthy and infected will be called eigenvector, because the population distribution does not change with time. Now let's plot this information on the graph. On x-axis we have healthy rabbits and on y-axis we have infected rabbits. On day 1, we had 5 infected and 95 healthy rabbits. So I plot this as a vector. On day 2, we had 13 infected and 87 healthy rabbits. Let's say on day 3, we had 20 infected and 80 healthy rabbits, so we plot that also. And this population of infected and healthy rabbits will keep changing till it reaches that steady state of where there are 70 healthy rabbits and 30 infected rabbits. So we plot that eigenvector with 70 healthy and 30 infected, and this is how it would look like. Now, let's say if the population of rabbits is still going through changes such that every day more rabbits are getting infected, then there will be more vectors to the left of this vector. In that case, this vector is not an eigenvector. Let's say the population stabilizes at 80 infected and 20 healthy, and the population distribution does not change after that. So this will be the eigenvector now. So in this example, an eigenvector represents steady state where both healthy and infected are in equilibrium. And this is why eigenvectors play a significant role in analyzing population dynamics, especially when using matrix models to track changes over time. An eigenvector in population models represent the steady state distribution, meaning that over time, population proportion among different groups remain unchanged. So looking at the graph, this vector is the eigenvector because it represents steady state distribution of population between infected and healthy rabbits. So how eigenvectors can be useful? Eigenvectors play a crucial role in predicting population dynamics in various real-life scenarios. In epidemiological models, an eigenvector might show how infections will propagate and whether a disease will die or persist. An eigenvector might show the proportions of susceptible, infected, and recovered individuals once the system reaches equilibrium. Eigenvectors help understand species interaction by using predator-prey model. They can reveal stable relationships between species by showing which population proportions will persist over time. In my next video, I will use matrices to illustrate the spread of viral infections in a community and how individuals transition between healthy and infected individuals. I will also calculate eigenvectors to show the population distribution and analyze the system. Hope this has been useful. Cheers.